Thank you for joining us for the IEEE Computer Society Standards webinar series, brought to you by the Standards Activities Board. With over 225 standards that transform the way we live, work, and communicate, the IEEE Computer Society sets the standard for design automation, simulation, testing technologies, Ethernet and Wi-Fi, quality assurance processes, systems architecture, DevOps, and more. Standards deliver best practice processes for developing market-ready interoperating systems, products, and services. You can have an impact by joining one of the over 200 IEEE Computer Society Standards working groups. Participating in one of the working groups grants you access to information that reduces risks, increases proficiency, and shapes the future of the industry. Help determine what's next in computing technology. Learn more about our standard working groups at computer.org/standards.
Okay, so hello everyone. Thank you for joining us today and welcome to today's webinars from our Standards Activity Board series and today's presentation from the Computer Society Functional Safety Standards Committee. My name is Edward O, and I'm the Vice President for Standards Activities of the IEEE Computer Society. Before we get started, I would like to adjust some housekeeping items. This webinar is being recorded. You can ask any questions in the Q&A box you see on your screen. The speakers will answer as many questions as possible after their presentations. When submitting any questions, it would be great if you can reference the slide. A copy of the slides and also the recorded webinars will be emailed to you tentatively tomorrow. Circling back to today's presentation, as some of you may know, the role of software in the safety critical systems continues to increase. The rate of failure from unknown defects in the software is unpredictable, thereby undermining the basis for the system safety hazard analysis methods that start from the point of a component or system failure. Besides, a system failure may have its origins in a one-time coincidence of two or more software design weaknesses. Altogether, control-oriented safety analysis fill a gap left by failure-oriented system analysis methods, particularly where the system of interest are software-intensive. And in the next 15 minutes or so, we will hear our expert of the Functional Safety Standard Committee on how the analysis fit with functional safety and system engineering. And now is the time to introduce our first guest speakers from the Functional Safety Committee. Our first speaker is Rob Shaw. Rob has extensive experience in software and system engineering. He has been with IBM and ITT in different technical and management positions. Nowadays, Rob serves as independent advisor to large corporations, depending on their capability to develop complex software-intensive systems, to use them in effective ways or to embed them in ever larger settings. In addition, Rob promotes a multidisciplinary approach, helping ensure stakeholders satisfaction with the outcomes of engineering. Our second speaker is Darren Galvin. Darren has worked for over 25 years in the semiconductor industry, working for ST Microelectronics, Infineon, Renesas, Sim5, and Samtec in roles which have included product engineering, verification, design, concept engineering, and natively functional safety. He is currently the chair of the IEEE Functional Safety Standard Committees, the IEEE Computer Society Treasurer, and the secretary of the draft IEEE Standards P3332, which is also the focus of this webinar. And our last speaker is Tom Font. Tom represents over 35 years focused on advanced software technology in control, monitoring, and diagnosis of industrial and infrastructure equipment. He is currently involved in proactive onboard equipment oversight and contingency handling for air, sea, and land autonomous mobility, as well as public infrastructure. As the last reminder, please note that as per the IEEE Standard Association Standard Board Operation Manuals, at webinars here, any individual presenting the information on the IEEE standards shall make it clear that their views should be considered as their personal views rather than the formal position explanation or interpretation of the IEEE. Now, I will give the floor to Rob to start the presentation. And once again, Rob, Darren, and Tom, welcome. Thank you for accepting our invitation to deliver this interesting scenario presentation. And Rob, please go ahead. Thank you so much.
Good day. This is Rob Schaaf. Thank you, Edward, for the introduction. Control-oriented system safety analysis. Today's presentation goes as follows. I start with a number of what-is questions, such as, for instance, what is control-oriented system safety analysis? After the what-is questions, we'll get into the core entities of the analysis, that is, the system of interest or the system under engineering, the operating environment, safety, harm, hazards, control, and unsafe control path. Next, we get into the heart of the analysis when we discuss how to find these unsafe control paths and the mandatory actions that represent the principles of control-oriented system safety analysis. After an intermediate summary, I hand the baton to Darren, who will talk about the analysis in the context of functional safety and specifically with reference to 26.26.2. Followed by Tom, who will talk about the analysis in the context of the system lifecycle and the system lifecycle processes as described in the 15.288 standards. Okay, before I go on, I have to make a first disclaimer. Edward already referred to that. When the three of us represent in any way an IEEE standard, these representations are ours and not IEEE's. Ours are not formal positions, explanations, or interpretations of IEEE. What you hear and see are personal views of IEEE standards. Now, before I go on to the what is part of the presentation, I have one more preamble. And that goes to the motivation of the control-oriented system safety analysis. The engineering challenge addressed by the analysis. The challenge is the difficulty in defining a complete set of safety-related requirements for software-intensive systems. This is the motivation behind the analysis. It's proven in practice very difficult to come up with a verifiably complete set of safety requirements. Systems that consist of many types of elements, but that certainly consist of substantial amount of algorithms and data, software. Requirements that play a critical role in the engineering of a system, in the development of a system. Control-oriented system safety analysis is meant to help in answering the challenge. By the way, a focus on software-intensive systems does not imply that the analysis won't work for other types of systems, systems without a lot of software. However, our mandate is to focus on software-intensive systems. I'll have more about the kind of systems in a moment. On to the what is questions and answers, the core entities that play a role in control-oriented system safety analysis and in the development of the standards for that analysis. And indeed, the first question is, what is control-oriented system safety analysis? It is a form of safety analysis complementary to other forms, and I emphasize complementary. This is not a replacement for any other type of safety analysis. Here, the analysis defined by a set of principles. These principles are part of system engineering and turned into actions. The outcome is a set of safety-related system requirements for the system of interest. In short, that is what control-oriented system safety analysis is. What is, you will hear about P3332. What is P3332? First of all, it's the label of a standard, the standard, IEEE standard for control-oriented system safety analysis. It's a standard, I emphasize, under development. P3332 also stands for a working group responsible for developing this standard. More, what is the objective of the standard? The objective is to present these principles that define the analysis. Principles and foundational rather than a particular method. And again, I emphasize the point, what you hear here is a set of principles, but not a complete method. A method is more than a set of principles. But these principles are industry and application agnostic. They inform and they are to be adopted for voluntary conformance by system engineering organizations and staff. Okay, what is the use of the standard? I already mentioned adoption for voluntary conformance by system engineering organizations and staff, but also independent subcontractors, as well as system integrators. The informative objective and use is for the whole broad audience. The users, the system operators, the regulatory and certification bodies, the suppliers, the acquirers, the trainers, assessors, the process engineers, quality assurance, method developers. I already mentioned principles that can be foundational to, for example, industry or application-specific methods. System engineering sponsors, the people that pay us to carry out these system engineering projects, as well as very much the stakeholders in addition to the system engineering staff and organizations. More what is. What is the status of the standard? The status is that the working group started in a year ago, nearly 2 years ago. The work is in progress, and the informal plan is not a confirmed plan, but the informal plan is to have a first ballot next year. Therefore, what you see here is not only speculative, things that you may hear today may not quite come out the same way in the ultimate standards. So it's speculative, but it's also, what you see here is the responsibility of the presenters and not so much the responsibility of the working group working on the standard. Okay, so much for the what is questions. Let's move on to the core entities that make up the body of the analysis. First of all, of course, we have the system of interest, SOE, the abbreviation. That system of interest is, as I already mentioned, safety critical and software intensive. As far as we are today, there's no constraint on the system type, except that we are actually quite certain that there will be some constraint on systems with AI elements. That is still very much a subject of discussion and will probably be conditioned in some way. But what they emphasize there is that safety is treated as situational, meaning that we are not looking at a system of interest on itself, but always in combination with an operating environment, OE. Now, a system of interest may have two or more distinct operating environments. That means that you have to work on these two or three distinct combinations as well. But I emphasize the fact that the control-oriented system safety analysis treats safety very much as situational. Moving on. We have safety, harm, and hazard. For safety, we start with a common sense and common dictionary definition, freedom from harm. For hazard, we use a quite often used definition, like in the IEC 61508 standard, potential source of harm. And for harm, again, we use the common dictionary definition, physical or mental damage. However, there's more to harm. The standard guides the user in defining harm with specificity for the cases at hand, ranging from very broadly, on the one hand, narrow, such as in loss of life or personal injuries, to broad, where harm may include a loss of reputation or privacy, damage to health, property, or the environment, and broader to the loss of reputation, of privacy, economic harm, harm to communities or social relations, supply chain disruptions, or public safety. Always limiting the defined harm for the case in question to what is strictly unacceptable. This analysis approach is not for somewhat acceptable harms. What we are after are strictly unacceptable harms. There we go. Sorry, we went to the one more core entity, and that is control. For control, we start with the common dictionary, power to influence or direct behavior. In the case of the combination of the software interests and the operating environment, the behavior is represented as a network of cause-effect change, a network with forks and joints, a network that also is referred to and very much referred to as the control structure for the particular software system of interest and operating environment combination. Now, in that network, there are presumably unsafe control paths, that is, cause-effect chain that leads to a potential source of harm. The system engineering objective then is to design the system without unsafe control path, designed to be taken in a very broad sense, and not only to include architecture and implementation, but also design where we are after the design of operating or use directions. Okay, now on to the heart of the matter. How to find unsafe control paths during this design broadly interpreted. And then upon finding unsafe control paths, what to do. First of all, develop for the system of interest and operating environment combination a network of cause-effect chains, the control structure. The construction of that network, the control structure, is a highly iterative affair, and so is what follows. In that control structure, locate a potential source of harm, then from that point, traverse the network backwards, and the emphasis is on backwards, starting from the potential source of harm. Stop that backward traversal when a point is reached in that network, in the control structure, where the system can be made to intervene and so avoid the unsafe control path. Make the system avoid the unsafe control path. Translate that intervention in terms of one or more system requirements, specifically safety-related system requirements. And finally, repeat the above for all the unsafe control paths and for all potential sources of harm. What you're looking at right here is the heart of the control-oriented system safety analysis approach. But the heart needs a body, a framework in which to operate. So next we go to that framework. And actually, these are the principles in the form of mandatory action, mandatory if one wants to conform to the control-oriented system safety analysis approach. Obviously, define the system and the environment under safety analysis. Define the stakeholders and their interests. Define the harm of interests. I already touched on that earlier. Identify the safety hazards. Quite the same way as other hazard analysis methods do. Identify the control structure, already referred to earlier. Identify the unsafe control path in that control structure. Define the corrective changes to the control structure by this backward traversal. Define the system-related system requirements. And then finally, also very much included in the standard is the point of verification and validation of the safety-related system requirements. I must emphasize that there is no meaning to the sequence of these actions. In fact, this is a very much an iterative affair where refinements, for example, in the system definition, can lead to refinements in the harm definition, where the formation, the definition of safety-related system requirements can make you go back to earlier definitions of the hazard, for example. All in all of this, the key word is iteration. In addition, I should say that, oops, 1, 2, there we go. No. Sorry, haha. Oh, why does it flips too easily? There we go. Well, there we go. The formulation of the activities in the standard is such that the standard provides enough specificity for a conformity assessment of a project against this particular standard. Okay, let me sum up what we have covered so far. Controls, when we speak about controls, it's not so much about control systems, but it's controls over safety hazards. That is, controls over potential sources of harm. The objective is no known path through the system of interest that can lead to potential sources of harm. Unsafe control paths are detected by constructing the control structure and by traversing this control structure in reverse, starting from a hazard. The backwards traversal to a suitable point of intervention where the unsafe control path can be cancelled systematically. Defining the intervention in terms of system requirements with a verification and validation of these requirements. Okay, this is my summary, intermediate summary. With that, I hand the baton to Darren, who will talk about the analysis in the context of functional safety. Darren, over to you.
Thank you, Rob. So specifically, we're going to look at how P3332 can be applied to ISO 26262 and specifically the functional safety within the automotive space. So functional safety is the part of the overall safety relating to the equipment under control and its control system, which depends on the correct functioning of the electrical and electronically safety related systems and other technology safety related systems and external reduction facilities, which means you've got the equipment which we want to make sure doesn't do anything dangerous, and we need things in place to help it stop it doing that. And the ISO 26262 applies these ideas to cars and defines what you're expected to do during the development and analysis of your equipment under control. And this definition is in the footnote on the slide, which is the Functional Safety Terminology Landscape, which is a white paper which was published by the Functional Safety Standards Committee last year. So when you are following the processes in ISO 26262, one of the first things it asks you to do is a hazard and risk assessment, which is more commonly known by the acronym HARA. For a system element out of context, and this is an idea where you are defining a semiconductor product which you are using for a given market or markets, and it's not application specific. So you are taking it to the market yourself. You need to perform the HARA. This is different to where a customer comes to you with a set of requirements saying what you need to do. They will have done the HARA in that case and come to you with the outcome of it. So when you are performing a HARA, you need to look at the potential hazards and categorize them based on 3 factors. And if you wish to see more detail on this, there is a link at the bottom which does a very good description of hazard and risk assessment methodologies. So you're looking at the severity of the potential harm of the hazardous event, the exposure of the operational situation of the hazardous event. So how badly could it go wrong? How many people and things could it affect? And the controllability of the hazardous event. And when you're doing your HARA, you come up with a rating for those three things. And it's a combination of that, which then tells you what the safety integrity level, or the automotive safety integrity level for ISO 26262 is, based on analyzing the context of the driving situations with respect to the categorizations you've come up with. You then need to construct a safety goal to avoid any unreasonable risk, and risk reduction or safety requirements are then derived from the safety goals, and this is where P3332 enters the scene. ISO 26262 also requires a fault tree analysis. So what happens if a fault occurs? What are the chance of monitors detecting or missing a fault? And a failure mode and effects analysis, where you look at what the system does with missing or unexpected events. So control-oriented system safety analysis for HARA. As per the previous slide, safety, harm and hazard, HARA defines what is unacceptable for the system. It then requires the user to identify from the interplay of mechanical, electronic and software systems what the network of control paths and cause-effect chains are. And the control-oriented system safety analysis takes the harm and works backwards through the control structure to find a decision node where an intervention could prevent the unsafe path from being taken. The analyzer then defines a safety-related system requirement to avoid the unsafe control path. Now, this could be an internal safety mechanism where we construct something within the hardware to keep us in a safe state. It could be an external safety mechanism where if this our hardware is used as part of a bigger system, the system detects that the hardware has gone wrong, or it could be software, which is periodically running something to check for the safe running of your system, or it could be a use case restriction where you tell the user they shall avoid using the device under certain conditions or in a certain way. Note that we are not defining what the requirement has to be, just what is necessary to avoid the unsafe control path. So this approach also allows for the idea of fail-safe or fail-degraded items where we end up in a safe state. So for fail-safe, we are not necessarily guaranteeing that we perform the function, but we do guarantee that we go into a safe state where we cannot do something which would generate harm. Or we have a fail-degraded outcome where we still maintain the function, but not necessarily with the performance that we would want if we were running without an issue. But what we are doing is guaranteeing we do end up in a safe state. So what the control-oriented system safety analysis does is making sure we are avoiding unsafe outcomes. But there is one caveat. That is where we take a control path with a less unacceptable outcome to avoid a worse outcome. For example, if we're going to crash, is it preferable to hit a wall, potentially injure the occupant of your vehicle, or hit a person if that person is in the way? Yeah. It doesn't mean that we never take an outcome with harm, but it's up to the owner of the system in that case to define what is the least acceptable harm. That's it from an ISO 26262 point of view. So, Tom, over to you. Thank you.
Thank you very much, Darren. We're essentially going to take a look at how a life cycle description of a system, which is what the 15288 standard is all about, and how does that essentially map into what we have been discussing before concerning the backward chaining technique that Rob mentioned, and how is that related to the life cycle management. But before we get into that, we're going to essentially give you a little background description on what is 15288 all about. Essentially, it's a series of processes that deal with agreement to develop or build a system, what is organizationally related to handle the project in order to bring that system to fruition. More specifically, what are the processes dealing with technical management that will define essentially the business cycle, essentially the workflow that will bring about the system, and finally the technical details of building the components of the system themselves, which are the technical processes. Who is essentially involved at each of these processes, these stages? And I think this little table sort of summarizes it. When it comes to agreement processes, we're talking about stakeholders, which essentially are users, customers, suppliers, who make an agreement with an entity to build a particular system. Then essentially the people in the organization involved with developing the system defines the structure needed to build that workflow that would lead to the development of the system. Technical management deals more with the details of the workflow that deal with that system, the actors being management, engineering, production, operation. And again, there's an overlap when it comes to the technical details because, again, engineering, production, operation are the ones that bring that system to life. So now, another way of looking at 15288 itself is as a kind of a cycle, where essentially we begin with an agreement, and this is where the agreement processes come into play, and essentially in a planning stage where essentially we define the organization and the organizational structure that will bring about that particular system into life. Next, we go into an analysis phase, where essentially dealing with the technical management, to some degree the technical aspect of how we're going to build this system all together. What's going to be the workflow required? What is the organization going to look like? And then next to a design and implementation phase, where we deal with the technical processes that build those components that actually become the elements, and in the integration of which become the elements of that particular system. And essentially this cycle repeats itself as a system grows, the life of the system is enhanced, and essentially you add new features to it based on, let's say, customer feedback and how to improve it. Let's say it's also in terms of field support and maintenance. How does the control-oriented system safety analysis play into this? Particularly in the analysis, design, implementation stages. And as you can see from this particular description, where we do in analysis is begin to identify the harm scenarios, where essentially could potential hazards crop up in the system. And when we get into designing the components themselves, well, we find essentially ways to mitigate or remove those particular harm scenarios that may occur in the system down the line. Finally, implementation, there are processes that are essentially in parallel to the system being developed that is used to support how the system operates. Things that there are tools that might be used during maintenance and so on, and how to essentially evolve new fixes or components to the system. And essentially want to prevent harm occurrence when these processes are being used in the field. So when essentially we have processes that update or essentially components of the system on the field, or essentially I needed to essentially bring a new feature into that particular aspect. And this will repeat on and on. You might think, for example, that, boy, this is adding more things to do as you build the system. And perhaps you're saying, well, this system doesn't have that long a life cycle. And, maybe we can lighten up essentially on some of these controls-oriented system safety analysis, but you never know. And an example of that, even though it's not a completely software system, is a certain aircraft that was built in the 1930s, DC-3. That picture was taken in 2024. It's a 90-year young system that with few additions and improvements, such as instead of piston engines, we have turboprop engines, and instead of analog instrumentation, we have digital avionics. We have essentially the functional product that essentially represents a system that can be readily used after a series of improvements and enhancements. So having that in mind, I'm going to pass it on to Rob, and you can take it away, Rob.
Thank you. Oops, too fast, previous. Summary. Safety as a matter of freedom from harm in the context of our analysis, specifically no known control paths that can lead to harm. A set of principles rather than a complete particular method. Tangible analysis outcomes in the form of safety-related system requirements, essential work products in the system lifecycle, complementary to other safety analysis approaches. A fit with system engineering and functional safety frameworks, and a foundation for industry and application-specific standards to come. With that, we complete the prepared part of the webinar. Over to you, Edward, for any questions.
Okay, thank you very much for your great overview of the latest standard development related to Java standards P3332, Rob, Darren, and Tom. As you mentioned, let us have a Q&A to answer a few questions from the audience before we conclude this webinar. I have a question that you also may see from the Q&A box. This is a question to Rob. So our audience has the following question. Company re-examining requirements for their validity. That is, the validation confirms that the requirements are correct, complete, consistent, unambiguous, verifiable. So the question to you from the audience is, what do you mean by verification of requirements? Because the audience point of view may be that company verification confirms that requirements have been certified.
So the question, the line, the audio line is not too sharp here. The question is about the verification of the requirements?
Correct. Why we need to do, what do you mean by the verification of requirements?
Okay. With that, I mean, and sorry for referring, but what you will see in the standard, and again, I'm talking here for myself, this is not the working group speaking, is very much the flavor of verification and validation as you find it in IEEE standard 1012, 1012. Applied, in this case, to safety-related system requirements. It's a formal process. And by the way, it does not mean that in order for the user to conform to 3332, you have to also conform to 1012. But we will take the essence of 1012 as it relates to the verification and validation of requirements. 1012 is much more than that. It's not only the verification and validation of requirements, but it's also of the verification and validation of architecture, of implementation, of use directions, etc. But we will take from that standard the essence as it applies to the verification and validation of safety requirements.
Thank you, Rob.
So there is, there is a reference there to another standard.
Okay,
Yeah.
great. Thank you, Rob, for the information. So the next question, perhaps either Tom or Darwin or Rob can answer, because you all are expert in the P3332. The question the audience asks is, will P3332 give guidance on how to describe or model the control structure on different levels of details?
The construction of what?
Okay, maybe you cannot hear clearly. So the audience asked, will the standard, I mean the P3332 you are currently leading, will that provide guidance on how to describe or how to model the control structure?
Not in our current plan. I myself, in personal experience, have relied very much on finite state machine representations. But at this moment, at least, we are not getting into method-specific parts. That may change, and like I said, I'm talking here for myself, but not in the plan at this moment.
Okay. Any comment from Darwin or Tom? Okay.
Nothing to add on.
Yes, Darwin, please.
Yeah.
Nothing to add to what Rob said.
Okay, I'm sorry. Go ahead, Darren.
No, that's it for me. Over you, Tom.
Okay. Basically, if you look carefully about what we're talking about over here, we're not getting into the realm of designing a control structure, but rather we're examining a control structure and making sure that there are no potentials in that control structure that would, or conditions that in the context of the operating environment would control harm. So there's an a priori need to have a prototypical or essentially initial control design that you want to follow, and making sure that that control structure, so put some guarantees there, will not lead to any kind of harm as defined by as we have defined in this presentation. So that's basically my comment.
Thank you, Tom. So the third question, I'm very sorry. The third question is actually they want to know the progress of your standard development, because the audience say rather you already have a job already for people to review or to ballot. So what is the current status of the P3332?
Okay, let me answer that question. The status is as follows. First of all, we have concentrated on describing the analysis in terms of action, in terms of process, if you like. My experience is with a topic like this, always start by focusing on the doing part. Yes, we are after the principles, but principles need to lead to action, and it's very clarifying in everyone's mind to start with that action. So in the standard itself, the standard consists of a number of clauses. I think we have laid out 6 clauses. And the action is addressed in clause 6. There are about 15 subclauses to that, each of them identifying a specific activity. And remember, the activities are standing for principles. An activity that in all of the 15 cases are then subdivided in tasks, activities and tasks. By the way, the layout of that clause 6 conforms to still another IEEE standard. I don't know the number from the top of my head, but it guides the developers of a standard in describing activities and tasks. Anyway, we have a complete draft of these 15 subclauses of clause 6. Very much up for review and very much up for constant reiteration. I'm a great believer in reiteration. You start with something that may not be too good, but only through feedback and discussion can things be made better. So we have clause 6 concentrating on the doing. Next to that, or before that, is a clause 5, which in a typical IEEE process standard deals with the concepts and explains the concepts and puts them in relation to each other. For clause 5, we have about 10 subclauses, and the progress so far is that, from the top of my head, I think we have 7 of the 10 subclauses written out, at least in drafts, up for working group review, feedback, change, discussion, etc. Working backwards in a typical process standard is in clause 4, which defines what it means to conform with this standard. Now, in that particular clause 4 does not yet exist in the draft of the 3332 standard as it stands today, but is somewhat it's not boilerplate, but it requires thinking. What does it mean to conform to this standard? When can we say, based on what evidence what is the necessary evidence that allows us to say, yes, we conform to this standard? Okay, still working backwards, we get to clause 3, which in a typical process standard is reserved for definitions. I'm not a very great believer in definitions. I could write a thesis maybe about definitions, but for me, definitions are a means of effective and efficient communication. They don't hide. For me, they are not much more than that. As I already showed in the presentation, we have some informal definitions. I would like to leave the sharper definitions, as you will find it in 3, until we really have a pretty good idea of what control-oriented system safety analysis is and what the concepts behind it is. So for me, that's why we started with clause 6 and are now doing clause 5. Anyway, working backwards, clause 2 is boilerplate. It's a clause that tells you whether or not, and if so, to what other standards this standard relies on in order to conform to the 3332 standard. As far as I know, there will not be mandatory reference standards for 3332. Yes, we will have very much an eye on several IEEE standards, but in order to conform to 3332, you do not have to conform to any other IEEE or ISO standard, or IEC standard for that matter. And then clause 1 is literally nothing else than what is called a project or authorization request, which are the marching orders, which is the brief for the working group. So that already exists. and has to be lifted into the document. Okay, so much for the status of the work product. It's very much a thing in progress, relies very, very much on iteration and feedback. Any follow-up question on that?
Okay, great, Rob. Thank you so much. Actually, the time check is we are already approaching the end of the webinars, and I understand there may be 2 more questions, but I don't think we can cover that. For the audience who may who submit the question, perhaps the best way is you can go to the P3332 website and contact our guest speakers and for follow-up questions. So at the end, it's a let us do the conclusion. So once again, I would like to thank Rob, Darren, and Tom for joining us today and sharing what is going on the Functional Safety Standard Committees, especially on the latest development on the job standards P3332. A quick programming note, our Computer Society will host a career-inspiring webinar later this week. If you would like to know more about how to improve collaboration, strengthen trust, increase accountability, and provide constructive feedback across your organization, please join this webinar at 11 a.m. Eastern Time this Thursday. For our standard activity boards, if you want to get the latest update from EqualToDoc3, especially on the standard development on 200 gigabits per second, 400 gigabits per second, 800 gigabits per second, and 1.6 terabits per second Ethernet solutions, please join our next monthly webinar on December 11. Once again, I would like to express my thanks to our guest speakers and also our society staff for joining us today, and for all of you, the participants, for joining us and for lively Q&A discussion. As mentioned, we will share with you the recorded webinars and the presentation slide later this week. Thank you again, and have a great rest of your day. The webinar is now concluded. Thank you.
Thank you.
Thank you.